Hello, everyone. This is a research presentation for IEEE CSPA 2022. Title of our presentation is Key Area Acquisition Training for Image-Based Plant Disease Diagnosis from Hosei University, Japan. So we have been investigating automated plant disease diagnosis since 2014. So we joined National Research Project and have collected approximately 300,000 precisely labeled plant disease images from 24 prefectures. So today's content is part of our result of this project. So according to report from United Nations, the plant disease and pest reduce yields by 20 to 40% of our food production. So early detection and appropriate treatment is quite important. However, for diagnosing plant disease, usually experts perform visual inspection, but usually those are expensive and limited availability. So a practical automated method have been called. So with the progress of recent deep learning technique, many diagnostic techniques for plant disease diagnosis have been proposed, and they reported promising performance, about 95 to 99% in accuracy. So those performance were achieved with relatively easy CNN models, such as BGG16 or ResNet50 model. However, most of conventional studies have serious problem on their evaluation. So that is, their real performance must be much lower than reported. So before step into the detail, we'd like to introduce the difficulty of plant disease diagnosis first. The plant disease image, as you can see, the symptoms of plant disease are often faint and vague. So those two images are cucumber leaf, but infected with same disease and collected from different farm. You can see those two looks very different. On the other hand, this image collected from the same farm, but infected with different disease. So you can see those two are quite similar. So you can see the plant disease diagnosis has a large covariate shift problem, and therefore easy to overfit to training data if the number of training data is not enough. So here is the example of strawberry image diagnosed with CNN model. So here is a heat map obtained by GradCon. The model not focus on a leaf region, this is a symptom, rather than the model focus on the background. So background usually have much larger area of symptom. So the model can overfit to those not important region. That is a problem. So for appropriate evaluation in automated plant diagnosis, the training image and evaluation image, test image, must be collected from different fields. But most of past study did not consider this. And recent study revealed that the diagnostic performance between from the same field and different field has a big gap between two results. The real performance is here, so much lower than reported performance. The last one is based on 221 kilo image, 221,000 images, and very reliable results. So we have a large gap between two results. So cutting edge CNN efficient V4 model plus data augmentation was not enough for plant disease diagnosis at this moment. On the other hand, CNN, the boundary box-based classifier, such as SSD YOLO and YOLO B345 and like that. So those models are robust to differences in distance to the target. So this model can simultaneously detect the location and contents. So promising technique, but you can see we need to make annotation before the training. So this is very, very stressful. So accordingly, we have a limited number of training data and leading the robustness issue. And another issue is those techniques require high resolution images at runtime. So the data is time consuming at runtime. So it is desirable if we consider the practicality in using at field. So we'd like to build a model with easy CNN-based model. So to make the model attention to the region of interest, several research have been proposed. So the anti-overheat training is a technique to segment out the region of interest, in this case, a leaf region in advance. They provided very good performance and very practical way using in automated diagnosis in field. But the problem is performing ROI segmentation at runtime as a preprocessing is time consuming. Okay. So here is another important base technique for our proposal, the stability training. The idea of stability training is if the input of two images is similar, the difference of two images are similar, the latent representation of the model fx and fx dash difference of those two is also small. So they add the penalty on the difference between the two latent representation to the original loss function to achieve this objective. This stability training can be applied to wide application and therefore used in many recent studies. So this is one of the base of our technique. So now we would like to introduce our proposal, key area acquisition training, in short, CAT. The CAT is a training strategy to make the predictor to obtain the same diagnosis result without ROI extraction at runtime as when it is performed. So the CAT is training method that make these results the same. Yes. So in sum, CAT leads the model's attention to ROI, region of interest. So thanks to this idea, CAT eliminates the time-consuming ROI extraction at one time, leading fast and accurate diagnosis. So if we apply the stability training directly to this scheme, so X and X prime here, but naive stability training did not work because the perturbation this is quite large. So this and this looks much different. So the hostility between this training and this training happened, and entire training did not go well. So that is a problem when we apply the stability training to our task. So we add additional supervised training to this and this, between this and this. So we can add the additional training term. So simply, originally this and this different. So we also supervise this to meet the target signal. This is our proposal in this very simple but effective proposal to attain the robust image-based plan diagnosis. So this term can be considered as data augmentation. So we add the supervised signal to also for this image. So for evaluation, we use 9-class cucumber disease diagnostic task. 5 are fungal disease and 3 are viral disease. So we use a total 77,000 training image, and for test image, we collected 9,000, roughly speaking, 9,000 leaf image from different field from the training images. So we compare the performance. We use efficient V4 CNN model with random augment. And we compare the baseline and pre-segmented ROI region, and then perform this model and perform stability training and the proposal card. So here is a summary of the diagnostic results. So as we can see, the proposed card improved diagnostic performance by 3.8% in macroF1 and 2% in accuracy. So this is better than AOP as performing ROI segmentation as a pre-processing here. So, and also the card did not increase the runtime from the baseline. That is, the card process at 25 images per second. On the other hand, if we perform ROI segmentation in advance, the processing speed is almost 1.1 image per second. That is very slow compared to the original. So baseline plus stability training show the lowest performance on our experiments. So in discussion, the proposed card improved diagnostic performance without increasing runtime. So that is, we see the downy mildew, corneosporus mold, and gummy stem blight, and bacterial spots. So those two typically increase the performance, and bacterial spot deteriorate the performance. So all of those symptoms, those disease have a granular symptom, and often, sometimes leaf lesion will die. So for those tasks, especially downy mildew and gummy stem blight significantly increase the performance. That is, we think ROI detection, ROI attention by card lead the model make appropriate attention to this region. On the other hand, bacterial spot has also granular spots, but some leaf, deadly leaf, can be rejected in ROI detection, so deteriorate the performance. And also, the white card provided better performance than without with ROI extraction in advance. So ROI extraction may lose important surrounding information, such as lighting condition or disease symptom. So this may lower the discrimination performance, but card utilize entire information with ROI attention. So that is why our proposal card showed better performance than ROI extraction in advance. And also, on the other hand, since card improved the performance 67 to 69, but this there is a big gap between this and the 99% from same population data set. This means that the cause of overfitting also exists in ROI as well as in the background. This means the ROI region, this region also includes the evidence of the field. So in the future, we need to apply domain adaptation or a similar technique to this task. But we have already experienced this is not so that easy task. Okay. As a conclusion, we provided new and effective training technique for image-based chronic disease diagnosis. The proposed card improved the diagnostic classification performance while did not increase the diagnostic time. We will continue to develop highly accurate and robust and fast diagnostic techniques. Thank you for watching this video.